In this video, you will learn about the ideal gas law. Look at this situation here. You have a cylinder and there is a piston over here. The piston is freely to move left to right without any friction over here. Now, the first question I will ask you is, how can I increase the volume over here? I want to increase the volume inside this chamber cylinder. Well, if you can pump gas into this cylinder, then you're going to push this piston to the right side because you can increase the volume. So volume is actually proportional to the amount of gas that is inside this chamber. Let's call that N, where N is number of moles. N is number of moles of molecule, gas molecule. So volume will be proportional to that. If I have to put a proportional constant, I'm going to call that constant C. So the volume is proportional to the number of moles of gas. Or I can write it this way. V divided by N divided by N is equal to a constant. And by the way, this is called the Avogadro's law. Is this the only way to expand the volume of the cylinder here? Probably not. Let's see what we can do. If we want to expand the volume over here, another alternative is just to heat it up. Based on our experience, by heating it up, because of thermal expansion, we can also expand the volume. So let's write it this way. V is proportional to the temperature. When you have higher temperature, yes, we can have higher volume. Another way of writing it is V divided by T is equal to C. By the way, this C is just a constant. It can be another constant, not the same constant. I just putting a C here. And this is called Charles' law. That means if you increase the temperature, you're going to increase the volume as well in order to keep the same proportional constant. Okay, let's look at the next one. What happens if I have this valve closed? No heating. If I just apply pressure over here, if I push this piston, what will happen with the volume? Well, if we compress it, the next time it's going to stay over here. That means when I increase the pressure over here, I would decrease the volume. In other words, pressure and volume is related, and P times V should be equal to a constant. What do I mean by that? That means if I increase the pressure, I have to decrease the volume in order to keep it balanced to be equal to a constant C. If I try to increase the pressure, if I try to increase the volume, what should I do? I have to decrease the pressure. Okay. So this one is called the Boyle's law. There is a way to combine all the Avogadro's law, Charles' law, and Boyle's law, and that is called the ideal gas law. Ideal gas law says P V over N T, that will be equal to a proportional constant R. If you look at this one, it's a combination of the Avogadro's law, Charles' law, and Boyle's law. Let's look at the unit of R. Pressure. The SI unit for pressure, it is Pascal. But in chemistry, usually we use the pressure atmosphere, AT ppm, that stands for atmosphere. As for volume, the SI unit for volume, it is cubic meter. However, in chemistry, we very often use liter. Over here, temperature, the unit will be Kelvin, and N, that's the number of mole, and the unit would be mole. And therefore, R should have the unit of atmosphere times liter divided by mole times K. The number over here, it is roughly 0.08206, and this will be the unit. This is called the ideal gas law. When I use the word ideal, that means sometimes some gas is not ideal. And what type of gas should be considered as ideal then? There are a few different things. First, the gas molecule should be very small, or we should say it has no significant volume. So the first point is no significant volume for the gas molecule. Okay. The second requirement will be they don't attract or repel each other. Okay. For example, if the gas, when they see each other, they combine together and then very easily will form a liquid, and that's not a gas anymore. Okay. So the second requirement is they don't attract and repel. Okay. And the preferred condition for the ideal gas will be low pressure and high temperature. That will be the ideal gas. Let me repeat again while you can say these two conditions over here. First, the gas molecule will have no significant volume. Okay. Secondly, the molecules, they don't attract or repel each other. And lastly, the ideal gas, the condition should be low pressure and at high temperature. Okay, let's try to do an example by using this ideal gas law. The gas law can be written in different ways. This is what you just seen. Or you can say that PV, that is equal to N times R times T. Just move the N and T to the other side. Okay, let's try this exercise. I would like to calculate the volume of a gas at 1 atmosphere and at 0 degrees Celsius, and that is 273.15 Kelvin, and that I have 1 mole of molecule. I would like to know what is the volume over here. And by the way, this condition, when it is at 1 atmosphere and 0 degrees Celsius, is called a standard temperature and pressure. It's called STP, standard temperature and pressure condition. I would like to know 1 mole of gas under the STP condition and see how much volume it can occupy. And by the way, when you look at this ideal gas law, what you can see is it is independent of the molecular weight of the gas. That means for all the gas, it will obey this law regardless of what gas it is. Okay, so let's plug in and see if we can calculate. So volume will be equal to N R T and divided by P. N is 1 mole, R it is 0.0 A206 with the unit ATM, liter, number of moles, and in Kelvin. Okay, so this one we have to multiply by the temperature that is at 0 degrees Celsius, but we don't multiply by 0 because temperature, when the gas constant, it is in the unit of Kelvin. We have to use the same unit, 273 K. That divided by, at this condition, 1 atmosphere. Okay, 1 mole over here, 1 mole. I'm omitting it, just have a mole. Okay, 1 mole of any gas, if I do the calculation, what I find out is it is equal to 22.4 liter. Okay, that means for any gas, regardless of what molecular weight, under the STP condition, any gas, 1 mole would take exactly 22.40 liter. Okay, so I round it off. So this one is independent of what gas it is. If you have a gas of oxygen, a gas of nitrogen, they all take the same volume. So it's a little bit more than like around a 5-gallon bucket. So that is a size of 22.4 liters. Okay, now let's look at an example now. Okay, let's look at number 21, for example. Okay, what is the pressure in a 3.41 liter container that has 0.741 mole of oxygen gas at 26 degrees Celsius? Okay, so let's look at our ideal gas law. PV equal to nRT. That is our ideal gas law, where R is the universal gas constant, and that is 0.08206 atmosphere, liter, divided by mole, Kelvin. Okay, so what are we looking for? It is, we are trying to solve for pressure. So pressure, P, will be equal to nRT divided by V. All right, so let's put every number in. If we have all the numbers in the same unit as the universal gas constant R, then we don't have to worry about anything. 26 degree, okay, so this one is not in the right unit. We have to convert 26C into Kelvin. How do we do that? That is equal to that number, 26 plus 273. Okay, so that I will get 299 Kelvin. Okay, so we have to convert all the parameters into the right unit. Next, we just have to plug in everything. If we plug in the numbers with this unit, so what we end up with is the pressure will be in the unit of atmosphere, ATM. Okay, N is the number of moles, that is 0.741 mole. R is this constant over here, so times 108,206. I will leave the unit for now. And T is the temperature, so times 299. And then divided by the volume, that is in liters, 3.41. What I get is, if I plug into my calculator, I get 5.34. And the unit will be in ATM. Okay, here you go.